I'm just going to sort of give you this formula set. You probably note that it's very, very similar to how we found the arc length using a regular rectangular function. So this is just a small change in the x component squared plus the small change in the y component squared, added together and square rooted. And then we just integrate each of those little tiny pieces. So this is just like using the distance formula, right? X squared plus y squared, or change in x squared plus change in y squared square rooted, summed together on very tiny little intervals on the very, very tiny little pieces that we get from a dx or from a dy. Okay? So this is the formula that we'll use for a parametric. Good or no?
Yeah.
All right, cool. So let's start with this one, which is finding the length of an asteroid. So if we want to find the length of this asteroid, and it's not an asteroid, this is a different thing, asteroid as opposed to asteroid. Let's first think about what this looks like. This is cosine cubed and sine cubed. And so we note, and I want to go back real quickly and note that dx dt and dy dt needed to be continuous functions, right? And also, we want to think about one of our rules from before that we said if we had any places where the derivative might be undefined, that causes an issue. We're going to have a similar thing going on with some of these parametric functions, where if we have a place where we have like a cusp, we're going to have to break it down. So before we do any extra work with this, I want to pull up Desmos and take a look. And hopefully, I think we talked about this graph at some point, but that's our x component, and our y component is sine t, sine t, sine t. And we're going to do this from 0 to 2 pi. And so we'll note that, let me zoom this in a little bit. We'll note that we've got cusps coming on at each of these different places. So like at pi over 2, there's a cusp. At pi, there's a cusp. At 3 pi over 2, there's a cusp. And at 2 pi or 0, there's also a cusp. And so in order to really go about this problem in the correct way, we need to break it down into each of these different little pieces. So this has one piece that goes from 0 to pi over 2, and we'll just do that one piece and multiply it by 4 to get the whole thing, since this is symmetric. Everybody see that?
Yep.
Yeah.
All right, cool. So it should be 4 times the integral from 0 to pi over 2. And we need to find then what dx dt and dy dt are. So what's dx dt?
-3 cosine squared t sine t.
And what about dy dt? Should be 3 sine squared t
Sine t.
cosine t. Yeah. And so now what we'll do is we'll just put each of those up into there squared. So if we square the dx dt, that's going to be 9 cosine to the 4th t sine to the 2nd t. And we'll add to that 9 sine to the 4th t cosine to the 2nd t. And it's all inside of a square root, and we'll put a dt at the end. Good or no?
Yeah.
Good. All right, so from there, we should be able to take the constant that's a 9 out, and factor a 9 out of both those terms, and pull it out of the square root, makes it a 3, and pull it out to the front, makes it a 12 out there. Everybody agree with that?
Indeed.
Perfect. All right, and then so now we've got 0 to pi over 2, 12, and what's going to happen with all of this? What can I factor out of this also and pull out of the square root?
Sine squared, cosine squared.
Sine squared and cosine squared, which when I pull them out of the square root will just become sine t and cosine t. And inside the square root, what's left from this first one? If I take out the 9 and a cosine squared and a sine squared, I just have a cosine squared. And if I take out the 9 and a sine squared and a cosine squared, I'm just left with a sine squared there. And cosine squared t plus sine squared t should be
Cosine. Well, 1. Never mind.
1, and when we square root that, that should still be 1. So really, we're just looking at 12 times the integral from 0 to pi over 2 of sine t cosine t dt. And 2 good ways to go about this one, or really 3 good ways to go about this one. What is one of the good ways to go about this one?
We could let u equal sine t, and then du is cosine t dt.
All right, so if u is sine t, then du, like you said, is cosine t dt. And that's going to change our limits also. So this is going to turn this into 12 times an integral from where to where? Sine of 0 is?
0 to 1.
At 0 and oops, 0 and sine of pi over 2, like you just said, is 1. And then it just becomes u and then du. So we've now got 12 times u squared over 2 from 0 to 1, which is what?
6.
6. So there are 6 units of length to this asteroid. Good or no?
What was the other way? Other
Well,
than that.
another way would have been letting u equal cosine and du being negative sine, which is a little bit not as good. The other way would be to say this is equal to 1/2 of sine 2t. And so just pull a 1/2 out here, make it 6 times the integral of sine 2t, and then you get 6 times the integral of 6 times 1/2, or negative 1/2 cosine 2t, and the value from there. Either way, any of those are fine. The way you chose is probably the easiest, but any of them are good.
Sounds good.
Any other questions on that one? All right, let's do another one. So we want to find the length of one arch of the cycloid that is given by x equals 2 times t minus sine t and y equals 2 times 1 minus cosine t. And so since I'm guessing most people are not super familiar with what that is, let's put it into Desmos. So we should have what we had. I'm just gonna distribute that out, 2t minus 2 sine t. And then the other one, if I distribute that, is just 2 minus 2 cosine t. And let's see, one arch, let's see, if I go 0 to pi, that's clearly not a full arch. Looks like 2 pi ought to do it, which makes sense, right? Because both of those are just t values on there, so it's going to repeat every 2 pi. And just to see what it does, if I throw in 4 pi there, it's just going to keep bouncing over and over and over this exact same thing. This is a cycloid. So we're going to go from 0 to 2 pi. Everybody good with that?
Absolutely.
All right. First off, before we go from 0 to 2 pi on this integral, we're going to need to find dx dt and dy dt. So what's dx dt going to be? The 2t will give us 2, and the negative 2 sine t ought to give us negative 2 cosine t. And then dy dt, the 2 ought to be 0, and the negative 2 cosine ought to become positive 2 sine t. Everybody good with that?
Yes.
All right, cool. We will integrate then from 0 to 2 pi, the square root of dx dt squared, which is going to be 4 minus 8 cosine t plus 4 cosine squared t plus 4 sine squared t dt. 4 cosine squared t plus 4 sine squared t ought to be
Just 4.
4.
And
So
you
that
can pull-
will give us what? 8 minus 8 cosine t dt inside of there. If I wanted to, we could pull out a 2 root 2 from that. And if I pull out the square root of 8, that's like 2 root 2, 0 to 2 pi. And then what would we have? We'd have a square root of 1 minus cosine t in there. And then what? How would we integrate that? Anybody have a good idea on that?
Maybe you could try using a power reducing formula, but like backwards.
Okay, so how would you do that?
Because then you'd make it sine, wait, which is sine squared 1/2 x, and then you'd have to I don't know. It's just a suggestion.
Yeah, something similar to that would sort of work out. This is not one that you'd be required to do on the AP test, but you could use the half angle formula, which is sort of very similar to the power reducing formula. Right, so if you were to try to use the half angle formula on, well, I guess it's power reducing. So your power reducing would be what? Or your half angle is what? Sorry. What's your half angle?
Sine of theta over 2 is equal to the square root of 1 minus cosine theta over 2.
Sine of x over 2 is equal to, sorry, say it again, square root of what? Sorry, no.
1 minus cosine x over 2. Like everything's over 2. Square root.
This one. Yeah. So that's basically what we've got here, except we don't have the 1/2 in here. Right. So if I were to put in that 1/2 there, we could do that. And if I put in the 1/2 inside of the square root, that means that I need to put in a
root 2 over 2. Or no, just root 2.
I need to put in a root 2. If I put in a root 2, that's going to put that in out here, which will turn that into a 4. And now I've got exactly this, sine x over 2. So I can turn that into 4 integral from 0 to 2 pi of sine of x over, or sine of t over 2 dt. Everybody see that? Hopefully. And what's the integral of sine of t over 2 when you integrate it?
-2 cosine t over 2. Something like that.
Not just something like that, but that.
Bracket.
And what does that give us? Gives us -8 times the cosine of pi. What's -8 times the cosine of pi? It should be 8, right?
8.
And then minus, and then another -8 times the cosine of 0, which is 1. So we get 8 minus -8, which is 16. Good or no? So using this
Yeah.
power reducing half angle stuff. Cool. All right. Similar basic concept there for a polar curve. So that's all we're going to do with the parametrics. The polars basically just end up exactly the same, right? Because we always just dealt with polar functions sort of like they were parametrics. We just have to take the, our function that we're given and turn it into an x or a y by making it multiplying it by either cosine theta if we're trying to find the x, or by sine theta if we're trying to find the y. So let's do one of these. Oops. Let's see if we can find the length of this cardioid. R equals 1 plus cosine theta. So what do we need to do? First, we need to find an x. What's x going to be?
Cosine theta plus cosine squared theta.
Sure, cosine theta plus cosine squared theta. And what's y going to be?
Sine theta plus cosine theta sine.
Sine theta plus sine theta cosine theta. All right, so what's dx d theta? Negative sine theta, right? And then what's the cosine squared theta?
Minus 2 cosine theta sine theta.
Minus 2 cosine theta sine theta, sure, you can write it that way, or minus sine 2 theta if you prefer. Dy d theta gives us what? Cosine theta, and then what's the derivative of sine theta cosine theta?
Cosine squared theta minus sine squared theta.
Yep, or cosine 2 theta if you prefer. But since you guys said them that way, we'll leave them that way. Then what? Then we just need to put it inside of an integral. A cardioid is going to have a cusp on it, so it's going to be better for us if we just do this from 0 to pi. That'll give us half of it, and we'll just multiply it by 2. So let's do 0 to pi of the integral of the square root of, and if we square this first one, let's see, negative sine times negative sine is just going to be sine squared. And then we're going to have plus, what are we going to have? Plus 4 sine squared theta cosine theta, and then plus 4 cosine squared theta sine squared theta. Everybody agree with that?
Would it have been easier to solve this if we had it for dx d theta instead of 2 cosine sine theta? We would have had it sine 2 theta.
Well, it's going to make what we're writing out a lot simpler, I would think, but
Okay.
it's a little late for that now, I guess. I mean, I guess we could, but. Now, you guys want to rewrite the cosine theta plus cosine squared theta minus sine squared theta as cosine theta plus cosine 2 theta?
Yes.
Okay. You want to go back and rewrite this one and redo it, or no? As minus sine 2 theta?
Nah.
No? Okay. All right. So what do we get here then? This one becomes plus cosine squared theta, and then plus 2 cosine theta cosine 2 theta. plus cosine squared 2 theta. Everyone agree with that?
Yep.
Yeah, okay. And what else we got going on in here that we can deal with? Any thoughts?
We have a sine squared and a cosine squared. in
Okay.
there.
So what's that
becomes
going
a
to give us?
1.
So that's a 1. So we end up with 2 times the integral from 0 to pi. One plus 4 sine squared theta cosine theta plus 4 cosine squared theta sine squared theta plus 2 cosine theta cosine 2 theta plus cosine squared 2 theta, all inside of a square root, d theta. And I bet if we'd turned this one, the first one, into sine 2 theta, is probably got to cancel out that cosine squared 2 theta if we'd wanted to. But since we didn't do that, it's a little bit messy to do that now. Hold on one second. So we can either throw this into the calculator or we can try and simplify it further. I'll leave it up to you guys. Okay, sounds like you want to simplify it further. So let's see if we can simplify it further then. What's 4 cosine squared theta sine squared theta? That's like having 2 cosine theta sine theta and another 2 cosine theta sine theta.
Yeah, it is.
What's that?
Sine of 2 theta.
And that'd be sine of 2 theta times sine of 2 theta, so sine squared 2 theta. So that'll cancel with this. So this will now make this 2 times the integral from 0 to pi of 2 plus 4 sine squared theta cosine theta plus 2 cosine theta cosine 2 theta d theta. Anybody see a good way to deal with that one?
There's another, the 4 sine squared theta cosine theta could be 2 sine 2 theta sine theta.
Okay.
And then we have like a 2 cosine theta cosine 2 theta.
So 2 plus this one, this sine, the 2 sine theta cosine theta would give us 2 sine theta sine 2 theta. That's what you're saying.
Yeah.
Plus 2 cosine theta cosine 2 theta d theta. Okay. Then what?
I don't know if this will help, but we can factor out that 2 and it'll become a root 2 on the outside.
Yeah, we could definitely do that. I think at this point, we'd probably end up having to like turn that cosine of 2 theta into like something different, something like 1 minus 2 sine squared theta or cosine squared minus sine squared, and try and distribute it. I think we're at a point where now it's probably best to just you're not going to have to do one this difficult on the AP test. Let's just throw this into our calculator and evaluate it. And let me know what you get when you do that.
8.
Same.
Sorry, say that again. What'd you get?
8.
8. All right. Cool. So must have been a way to find a nice way to simplify that down. But I don't think that's to our benefit to try and do that at the moment. So good enough? Conceptually okay?
Conceptually, okay.
All right, that's my biggest concern. I want to make sure we're good conceptually. So, all right, last thing would be if we had vectors that we were trying to figure out stuff with. And so I'll let you guys read through this first rather than me just like rambling about it. And then after you've read through it, we'll talk and make sure there's no questions or anything. And I'll make sure we're good. So take a second, read through that, and then we'll talk about it. Right. Still be able to find the distance a particle travels in a plane. All right, everybody good there with reading that?
Yeah.
So basically all this is saying is, we know that we can get a displacement vector. I think we could probably intuitively understand that since we took a derivative of a position vector to get a velocity vector. If we integrate a velocity vector, it's a position vector or displacement vector. Same thing. And we can just, find an actual position at our new time by adding that to wherever we were at A. And if we want to look for the actual distance traveled, we're going to use this same distance formula type arc length thing with a square root of V1 squared plus V2 squared. And that's like integrating the absolute value of the velocity, right? That's what should give us the actual distance traveled. Good or no? Anybody have any questions on that, or are we okay with that and can do a problem and feel all right about it?
Yeah, it's all simple enough.
Okay. All right, so suppose we've got a particle that's moving in the plane that has a velocity vector of t minus 3 pi cosine pi t, 2t minus pi sine pi t. And we know that at t equals 0, the particle is at the point 1, 5. How would we find the position of the particle at t equals 4? What would we do?
We would like integrate from 0 to 4 and then add that to 1, 5.
Okay, so let's do that. So we'll integrate from 0 to 4, and we're going to do that for both of these, right? So if we'll do it for t minus 3 pi cosine pi t dt. And what do we get if we integrate t minus 3 pi cosine pi t dt from 0 to 4? What is the actual integral of that? The t gives us a t squared over 2, right? And then the 3 pi cosine pi t, we'll throw a 1 over pi in front of it, so that just becomes minus 3 sine pi t. Everybody agree with that?
Yeah.
Okay, from 0 to 4. And what do we get if we do that then? Plug in your 4, that's 8, right? Minus 4 pi, sine of 4 pi is 0. And then minus 0, minus 0. So the change in our x component is positive 8. And so then we'll do it for our y component. So we'll integrate, what was it, 2t minus pi sine pi t dt from 0 to 4. And what is the integral of 2t minus pi sine pi t? That should just be t squared. And then what? Plus, it's negative sign, and then the 1 over pi that gets thrown out there cancels that out. T squared plus cosine pi t. Good or no?
Yeah.
And we get 16 plus the cosine of 4 pi, so 16 plus 1 minus 0 plus 1. So our y component will add 16 and our x component will add 8. And so we are at the point 1 plus 8, comma 5 plus 16, or 921. Good or no?
Pretty.
All right. Now, what if I asked you then for the total distance that our particle traveled from t equals 0 to t equals 4?
Then we take the integral from 0 to 4 of the square root of each of those functions squared.
Integral 0 to 4 of what? Of our velocity component squared, so t minus 3 pi cosine t, sorry, cosine pi t squared, no derivatives needed, right? Plus 2t minus pi sine pi t, because we've already got velocity functions squared dt. And that one, we're not even going to bother to try and simplify that garbage out. Just approximate that one on your calculator. What do we get? Anybody? Making sure you're in radians.
Did anyone get 33.533-ish? Or am I just being dumb?
I don't know, but I'll write it down in the hopes that somebody else also gets that. Anybody else get 33.533? That seems reasonable.
Yes.
Yeah. Yeah, because I mean, we know this is not going in a normal trajectory. I mean, it's not going straight from 1.5 to 921. I mean, clearly, because it's got a bunch of pi's and cosines and sines and all that junk in there. In fact, this is what the path it takes looks like. It goes from that initial point at t equals, what was it? Was it t equals 0, right? Yeah, it's at the point 1,5. And it goes along this path here to get to its final point at, what was it, 921. So if you look just from like 0 to 1, you can see it's doing, let's see here, 0 to 0.5, we're getting something like this. That's why this is a velocity. Oh, that's our velocity one, huh? That's not what we should be looking at anyway. Bummer. All right, what were our integrals?
Can you make it go to like 100 just so we can see it?
Oh, sure. This is just the velocity, though.
Yeah.
I accidentally typed in the velocity instead of the position function.
That's
Right.
pretty cool.
Oh, yeah, it's very cool. Sorry, I should have typed in the position though. So it's at t, we had t squared over 2, and then what was it, minus 3
Sine pi t.
3 sine pi t, and
T squared
squared.
plus pi t.
So looks like this.
That's even cooler.
Even cooler. So it starts actually here at 1,5. Now this is 0 to, so it's yeah, well, it's not quite going to look like this, but this is the path it takes right here along that trajectory to get up to our final point. Kind of cool. All right, we got some more stuff we got to do though, so let's stop playing around in Desmos. We got to start talking about these new things called improper integrals. And so everything we've dealt with so far in terms of integrals, while it may have been a pain on occasion, it was always with like whole number values, right? Real number values that we'd integrate from 2 to 7, or we'd integrate from -1 to -0.5 or something like that. We'd never have anything where we might have to integrate going towards infinity, or where we might be integrating towards a vertical asymptote or something like that. And so that's what we're going to start dealing with. We're going to do a little bit of it right now. We're going to finish it up, I hope, tomorrow or Monday. But we're going to talk about how to integrate at infinite discontinuities and how to integrate going towards positive or negative infinity. And anytime you do this, for example, in a problem like this, it's called an improper integral. And so an improper integral is any integral that has an infinite limit of integration. So if I'm going from some constant to infinity, or if I'm going from negative infinity to some constant, or if I'm going from negative infinity to infinity. And so the official way that we do this, because we technically cannot do an integral at infinity, is we just substitute out that infinity with some variable b or a or c or q or whatever you really want it to be. It doesn't matter what you choose. And instead of doing the integral from a to infinity, you'll do a limit as b approaches infinity of an integral from a to b. And we will look and investigate at what happens to that limit as it goes towards infinity. And we'll do the same if we're going for negative infinity to some constant. We'll just do the limit as a approaches negative infinity of the integral from a to b. And if we do negative infinity to infinity, we choose a point in the middle that makes sense and is reasonable, and we integrate from the left from negative infinity using a limit, and then to the right using a limit towards infinity. So we'll just do each of those one time. So this is going to allow us to find out if the area under some curve, so let me actually go, I said we were going to be done playing around in Desmos, but I lied. If some curve, like for example 1 over x, if there is a finite amount of area underneath this, let's say from 2 to infinity, because we know what does this do? It approaches 0, right? There is a limit of the function as we go towards infinity. The question is there a limit to the area, or is there an infinite amount of area? And we could do the same kind of thing with something like 1 over x squared or 1 over x cubed, right? And see, obviously the amount of area underneath each of these as we go from, let's just say 1 to infinity, it looks like it's getting smaller, right? With each extra 1 that I put in there, a little bit less area. Is there a place where we can find the area and a place where we can't, where there's an infinite amount of area? And even if I did something like x to the 1/2, right? This is still going down here and getting very, very small, right? Still approaching 0. Is there an infinite amount of area, or is there a finite amount of area? And that's,
why wouldn't there be an infinite amount of area?
well, because sometimes there's not.
Okay.
Yeah, and this is where, and I would say that everything we've done, okay, so you made the leap of faith, like when you first started calculus, and said, all right, we're going to do these limits and we're going to look at what's happening as we go towards infinity. Well, you said something like, well, what's the limit as x approaches infinity of 1 over x, right? Well, what's that limit? It's 0, right? That doesn't mean that we get to 0, right? Because we don't get to 0, but that limit is 0. That's what we're approaching, right? Well, it's the same thing with this area. Is there a limit to what that area approaches? Does the amount of space underneath this curve, as I, go way out here towards, I know this isn't anywhere close to infinity, but like there's still space under that curve. As I go way out here towards infinity, is there a limit to the amount of area that I'm adding into this, or is there not? That's the question we're going to be looking at. It's the same kind of idea, but this sort of at this point is where things start to get a little bit funky. I don't know. Funky is not really the right word, but things are not as they might seem, and we get some very odd and interesting results that we will hopefully talk about tomorrow. But if not tomorrow, we'll talk about them on Monday. But yeah, I can't give you a good answer for why wouldn't there be an infinite amount of area, other than there isn't sometimes. Sometimes there's a finite amount of area there. So, sorry. Math says that there is a limit to the amount of area under some of those curves. So conceptually, do you understand what we're going to do with the integrals and the limits? Or no?
Probably.
Okay, so what we will then say is that if the limit that we find, and we're going to start with doing this one for e to the x, if the limit that we get is a finite value, then it means that the improper integral converges. Okay? If the limit that we get doesn't exist, we say that the improper integral diverges. Okay? And for the third case, like if both of the limits, so like in our third case down here where we're doing negative infinity to infinity, if both of the limits are finite, then the improper integral, we say it converges. But if one part or the other doesn't exist for the limit, then we say that that improper integral diverges. And so diverges just means that the amount of area underneath this thing is infinite. Converges means that there's a finite amount of area underneath this curve. So important terminology between converge and diverge. Converge means there's a finite amount of space. Diverge means there is not a finite amount of space. There's an infinite amount of area underneath it. So let's see if we can do this with negative infinity to infinity for e to the x. So where do you think is a good place to break this up between negative infinity and infinity?
C.
Well, we gotta come up with some number. So where do we want to break it up? Again, it's got to be an actual number. We could use C, but it's much more helpful to use an actual number.
How about 0?
0 sounds good. So let's go with, this is the same as the integral from negative infinity to 0 of e to the x dx plus the integral from 0 to infinity of e to the x dx. So what we're going to do is now we're going to look at each of these separately. So first, I'm going to look at this one, the integral from 0 to infinity of e to the x. And I hope right off the bat you can tell me, is there a finite or infinite amount of space underneath this?
Should be infinite.
Should be infinite just because you know what this function is. But let's show it anyway. So what would we write? We'd write a limit as, doesn't matter what variable you will use, we'll say a. The limit is a approaches infinity of the integral from 0 to a of e to the x dx. Well, what's the integral of e to the x? It's
E to the x.
It's just e to the x. So we have the limit as a approaches infinity of e to the x evaluated from 0 to a. So what we do is we plug in a and we plug in 0 and we write it out. So we get the limit as a approaches infinity of e to the a minus e to the 0, or the limit as a approaches infinity of e to the a minus 1, which is e to the infinity minus 1, or infinite, right? This came out to be infinity, which means that that limit technically doesn't exist, which means that this diverges. Okay. Now, immediately, that means we don't need to look at this piece of it. But just for the sake of practice, let's look at the other side of it. We would do a limit as, let's say, b approaches negative infinity of an integral from b to 0 of e to the x dx. And what would that give us? Should just be a limit as b approaches negative infinity of e to the x from b to 0, which is what? E to the 0, or 1, minus e to the b. Everyone agree with that?
Yeah.
Which gives us 1 minus what?
0.
1 minus 0, or 1. So on this side, we got a finite amount of area. On this side, we got that there's an infinite amount of area, so it diverges. So we would then say that this integral itself diverges. But it's an interesting thing to note that what do we know about the e to the x function? As we go towards negative infinity, what does it have going on? It's got
A horizontal asymptote.
got a horizontal asymptote. We're approaching 0, right? But what this is saying is that if I were to look for all of the area underneath this curve from negative infinity all the way until I got to 0 and cut off right here, vertically straight down at 0, this area, which earlier, I think, Noah, you told me, well, of course there's an infinite amount of area underneath those because it goes on forever. Well, no.
I said, why
There's
wouldn't
not.
there?
What?
I said, why wouldn't there be? I didn't make a statement. I made a question.
Okay, cool. So you said, gosh, why wouldn't there be? Of course there would be. It's clear that there would be an infinite amount of area. Those were exact words, I remember them. And now we've shown that from negative infinity to 0, there is exactly 1 unit of area underneath the curve e to the x. Even though it extends forever and there is always extra stuff that we're adding in, well, no, there's not actually, technically. Eventually we're adding in so little that it's effectively 0, and that we have exactly 1 area underneath this curve. Good or no?
Good.
Yeah. It's like, you take a half and a half plus a fourth plus an eighth plus a 16th, right? And you just add them all up, right? Well, what are you eventually approaching?
0.
No, you'd be approaching 1/2 plus 4th plus an 8th.
Oh, the sum. Yeah. Okay.
Yeah. If you subtracted them, yes. If you subtracted them, you would be getting towards 0. But it's the same kind of concept, right? I mean, do we ever get there? No, but do we? Well, yeah. If we go infinitely, we do. And so that's this whole idea of infinity is so powerful in all of math, from calculus and beyond. The idea of infinity is just like, it's something that you just sort of have to wrap your head around and sort of start to understand that infinity is infinity, but like, I don't know, it gets weird. We're not going to get too much into it right now. Let's go back and do another problem. Any questions on the one we just did?
On an AP test, if we did something like this, would we have to do both parts, or can we only do the first part like we did and then just say it diverges?
Yeah, just doing the first part would be fine, because that would show that it was divergent in total that it was divergent. That'd be fine. I just wanted to illustrate this because Noah was so sure of himself that there was no way to have a finite amount of area underneath a curve that extends indefinitely above the x-axis. So, all right, let's do a couple more. So if we want to look at 1/x, which is the one I think I first graphed on Desmos a while ago, and look at it from 1 to infinity, what would the limit that we would write for this one be? Should be a limit as what variable do you want to choose?
A.
Sure, that's fine. As a approaches infinity of the integral from 1 to a of 1/x dx. So this should become what? The limit as a approaches infinity of what? Natural log absolute value of x from 1 to a, which gives us the limit as a approaches infinity of natural log of, well, if a is going towards infinity, that absolute value is kind of insignificant, right? Natural log of a minus natural log of 1, which gives us the limit as a approaches infinity of natural log of a, right? What's that become? That becomes natural log of infinity, which is infinity. And so we would say that this integral diverges. That underneath the curve 1/x from 1 to infinity, there is an infinite amount of area. So that one, it is not finite. There is always more and more and more and more area. Good or no?
Yeah.
All right. What about this one? Let's do a limit as, anybody got a variable they want?
B.
B, ooh, switching it up. The limit is b approaches infinity of the integral from 1 to b of 2/x cubed dx. That ought to become the limit is b approaches infinity of, well, what's the integral of 2/x cubed? That's 2x to the -3, right? So go up to -2 and divide. What do we get? We get negative 1/x squared, and negative 1/x squared. Or negative x to the -2 if you prefer, from 1 to b. Good or no? And that gives us what? Negative 1/b squared minus negative 1/1. And if we were to go in and evaluate this limit as b approaches infinity, what do we get? We get 0 plus 1, which is 1, which tells us that underneath 2/x cubed from 1 to infinity, there is, once again, exactly 1 unit of area. Good or no?
This may be a silly question, but for the first one, 1 over x, it has a horizontal asymptote
Mhm.
going from 1 to infinity. So is a horizontal asymptote not a condition for a converging thing, or?
Nope, not necessarily. It could have a horizontal asymptote and it could diverge, or it could have a horizontal asymptote and it could converge. Right? They both have the same horizontal asymptote, right? They both have a horizontal asymptote of y equals 0 as x goes towards infinity. Right? As we go towards the right, both of them do.
Yeah.
But one of them diverges and the other one converges to a value of 1.
Is it worth asking why, or is it just that's how it is?
It's worth asking why, but it's not worth asking why right now. We will prove this for at least for these are called p-series functions, and we're going to talk about these when we talk about series. And well, I would say in 2 or 3 weeks, but really it'll be in like 10 weeks. And we will prove, or we will use some stuff that we know about series once we start learning about series to prove a value at which the power in the denominator here of something like this will give us a convergent or a divergent integral, or in fact, we also will call them convergent or divergent series. So it's not a question we can answer yet, but it's a good question.
Okay, cool.
We will answer it this school year. Just not yet. Brian, I saw your question in the chat. Yeah, you can, any letter, it doesn't matter. I know I put A's and B's in the thing, but you call it Q or Z or whatever you want to call it, doesn't matter, any variable's fine. But yeah, does that answer your question? Yes, that's a great question. And we can't, I mean, we could demonstrate enough values to have a really good idea of where that cutoff point is, but that wouldn't be a proof as such. There's a big difference between a proof and a demonstration of something. So we could demonstrate where we think that cutoff point would be between the powers, but the powers of these, what we call p-series functions, which is just a constant over x to the p power. So this is 1 over x to the first. This is effectively 1 over x to the third, where p is equal to 3. They're both p-series functions. But does that answer your question or no?
Yes, thank you.
Okay. So don't worry, we will learn much more about this, because these improper integrals are really taking us into the point where we can start thinking about series. So, all right, that's where we're going to stop, because we're not going to have enough time to do the next one. So tomorrow we're going to finish up as much as we can with improper integrals, and Monday as well, because we got some cool other stuff to, or no, Monday's a holiday, right? So Tuesday. Yeah, so we'll finish up improper integrals hopefully on Tuesday. The arc length stuff should all be possible for you to complete now, I hope. And I will put up something for improper integrals in the next, either tonight or tomorrow, for you guys to work on, but it won't be due till sometime through next week. Next week, Wednesday, we'll have an arc length quiz. And then Friday, we'll have a quiz on everything else that's left. And tomorrow we have a quiz solely on volume. It will probably only be like 2 or 3 questions, and I hope that it will go quickly because I want to have more time to cover more material. Any questions on any of the improper integral stuff? All right.